So what I'm going to be talking about today is a family of techniques that we call Monte Carlo techniques, and I will go into why in a minute. But the idea is that sometimes there are processes that are very difficult to simplify down to an analytical model, right? They're difficult to describe mathematically in a simple enough way to model. And so the easier thing to do is to define your weird whatever boundary conditions and generate a whole lot of random numbers and simulate the processes or process that you're interested in as an ensemble, sort of randomly varying events about some probability distribution that you can describe. So just as a start off, I'm going to give just a little bit of an overview in lecture mode, and then we're going to spend most of the rest of the lecture looking at some interactive demo codes that I set up, and they're all MATLAB live scripts. And just to give you a head start, if you want to, I think, is there a link on the schedule yet? Or okay, so sort of as I talk through, go ahead and get those files down onto your computer if you'd like to follow along. They're in the student Google Share Drive. There's a subfolder I made called the code for lecture 30 Monte Carlo. And in there's 3 folders, _1, 2, 3 is the start of the folder names, and just copy them all down. They're all independent of one another, but there's a different example in each one. Okay, so Monte Carlo techniques, again, is this set of modeling techniques that are based on randomly simulating collections of events. And in this case, we're going to mostly be talking about collections of photons and making them interact with different sensors or water systems or whatever. But you can use it for all kinds of things, including simple things like error propagation. They're called Monte Carlo techniques because you roll the dice, right? You're generating lots of random numbers to simulate whatever it is that you're trying to model. This apparently is what the inside of a casino in Monte Carlo looks like. I've never been there. I don't know, but that's what the internet says. There is also a really cool, simple discussion of dice rolling games and how Monte Carlo works that Patrick forwarded to me over the weekend. At the towardddatascience.com blog. So if you want to check that out, it's also in Python. Everything I'm going to show you is in MATLAB. So if you just want to sort of see some of the base important functions. So we're going to start off. I'll just talk you through how all this works and then walk through those 3 examples. Okay, so the general premise of a Monte Carlo simulation is that you have some event or some collection of events that's taking place in the system you're trying to model. And you map the probability distribution of each event that's taking place in your system onto a 0 to 1 distribution. And then you use the random number generator in your computer to generate numbers between 0 and 1. So you are basically drawing outcomes using these random numbers, depending on the probability distribution of what's happening. So you repeat this, obviously, many, many, many times until the ensemble starts to predict what might actually happen in your real system. What I'm going to do is make a little flow chart of how a Monte Carlo model might work for putting light into a homogeneous fluid medium with known IOPs. And as I step through this, start thinking to yourself, okay, in the simple hypothetical model, what are the different probability distributions that we might want to know to map onto this random number interval? So if we start off in our medium with known IOPs, and we want to model what happens when a photon goes into that, or when light goes into that medium. We're going to start by generating a photon with some location and some direction. And then we're going to move it into the medium. We're going to move it through some distance dz. And the only constraint is that dz needs to be a lot smaller than 1 over the beam attenuation coefficient, right? So you're sort of infinitesimally moving your photon into your medium. And then in your model, you want to find out, okay, after this photon has moved to dz, is it then absorbed by the medium, scattered, or neither? So here, three potential outcomes. One is neither, right? So then we move the photon again, some infinitesimally small amount relative to the beam attenuation coefficient, and start the loop over again. Oops. We could find that the photon has been scattered. At this point, it's moved to, in which case we have to give it a new direction. right? And then move it again in its new direction, another increment dt. And then the third consequence is that it could be absorbed, right? The photon dies, we stop modeling it at that point, record potentially, if we care, where it died. And then, oh, have we made enough photons yet? We've modeled one at this point. And if we're trying to actually model light in water, we're going to need a lot more than one, right? And so if we have not, then we start the loop over again, right? And if we have, then we end the simulation. So this is the basis of a very simple, very, as you'll see, computationally inefficient Monte Carlo simulation. But it's sort of a nice just thought experiment. If you haven't thought about modeling things in this way before, this is kind of a real basic, how does it work? So if we have this hypothetical model, this flow chart I've just put up here, what probability distributions should we include in our model? What do we need to represent over this 0 to 1 interval to choose from random numbers? If it's absorbed? Okay, hang on. My pencil is not paired with my iPad. Let's try again. Okay, absorbed, scattered, probability. Okay, so when we have an attenuation event, is it absorption? Is it scattering? Yep. What else do we need to know? Okay, so which direction does it scatter? Okay, what did we call that? And we're talking about the yeah. We need the volume scattering function of our medium. Okay. What else? Transmission. Okay, so say beam attenuation. Right, that's going to help us decide how far DZ has to be. What about the properties of the photon that comes in? Okay, so you can say wavelength. All of this you could just do at a single wavelength, but those are going to affect all of those, right?
Mean cosine.
Mean cosine. Okay, so radiance, angular distribution. Same thing, direction. Okay, so direction of the light, maybe the distribution of the light. If you were trying to model in 2 dimensions, you're just modeling in 1, it doesn't matter. Intensity. Okay, so what would that map to in here? Number of photons, maybe? Okay. Good. So we sort of thought through, okay, what are these things we need to know? And each one of these has to be represented as a probability distribution. Okay, so initial direction of photon, location of photon, how far it goes between attenuation events. And the way we're going to do this in these models, rather than moving the photon a little bit, that's a random distance, checking if it's attenuated, moving it a little bit more, that's very inefficient. So instead, we just model this distance between attenuation events as minus log of a random number between 0 and 1 over the beam attenuation coefficient. So basically, in the model, we move the photon until it hits an attenuation. And then we decide if it's absorbed or scattered. We'll move it again till the next attenuation, etc. So when it occurs, whether the photon's absorbed or lost or scattered, right? We didn't talk at all about boundaries, but you could model. I'll show you an example of modeling boundaries, like does it hit a wall or a sensor at the bottom or go back out, right? There's all kinds of additional things that go in, but you know, when that happens, what are the IOPs of the event? And then the direction of scattering. Great. Okay, so this is specifically for a Monte Carlo model of light propagating in water. Very, very simple case. We wouldn't necessarily really need to use Monte Carlo modeling, right? In a simple plane parallel, known IOPs, no radiance distribution, right? But what if you don't have a plane parallel system? What if you're trying to model, as I'll show you later, photons in a beaker of water? I did a lot of this when I was a grad student. Or what if you want to model the shadowing of the sensor by the platform or the frame that you've attached it to, or model the shadowing of a radiometer by a ship, right? These are situations where you've got asymmetry in the medium, in the environment, that you might want to model. So it's really useful sometimes to use Monte Carlo models to take care of those kinds of systems. You can also use it for sensitivity testing, for error propagation. My most recent use of Monte Carlo modeling was tracking sinking particles through turbulence, because I was curious. It wasn't light at all, right? But it was just a situation where you just I needed to simulate a population of things and what happens to them under conditions that were otherwise difficult to fold into the model.
I feel like that thing with the polarization, which I think is hard on the back. Some of these models.
Yeah. So it's very flexible. Like you can put in whatever properties you want. So what we're going to do is step through some examples, and the goal is just to help you build intuition about how these models work. Some of the examples I'll show you are more elegant than others. One of them I wrote when I was in grad school, and it is an example of slow, inefficient, but it made sense to my brain at the time. And if you're starting out, sometimes that's a good way to go. And then I'll show you a more efficient, elegant, sort of homogeneous radiative transfer model that was written back in the 80s, when you really did have to be efficient and elegant, or your code would take too long to run. We have an advantage now that it's very easy to simulate millions of events and do it fast. Okay. So 3 examples we'll go through. The first one is actually just an extension of the particle size distribution fitting, power law fitting code that I showed you 2 weeks ago. Only this time we're going to propagate uncertainty in the particle counts into the particle size distribution slope using Monte Carlo. So that's very, very kind of initially straightforward. And I'll show you this modeling photons in a beaker in a non-plane parallel situation, and stepping up from 2 dimensions with no boundaries to 2 dimensions with boundaries to 3 dimensions with boundaries. And then finally, we'll look at a model. This is the one that was written in the 80s. That's very elegant and fast. And you guys can play around with that one more after this is over if you'd like to. So this is where it lives. Everybody have it that wants it? Okay. Right. Okay, so this is the live script. It's in the first folder, so it's the backup. This is the example that is in the folder that the file name starts with 1_, and now I can't remember what I've called it. Error propagation, something like that. So you will want to, I will want my computer to not be frozen. There we go. So you'll want to load up the script that is process IFCB PSD MC examp MLX. And there is a regular M file version of this if you would rather just go fast and do it on your own. So the beginning part of this, I've taken out all the section breaks. It's exactly what we ran before. So it is going to read in the size information, particle size information, counting information from an IFCB data file, and go through and do everything we did 2 weeks ago. So I'm going to scan all down. So I'm going to run that part. And that's going to bring us to the section that starts on line 143. And it's already not happy with me. Why not? Sorry, apparently I did not take out all of the section breaks. So you'll want to run things all the way. So start at the top, and I still have an error, but I think that's because I tried to run the other thing. Here we go. plotted, right? We resampled the data, plot the resample data. Good, now we're happy. Okay. So what we've done, just as a reminder at this point, is we have taken particle size data, binned them into log space bins, computed the counting uncertainty within each bin based on Poisson statistics. That's what these error bars are in the plot here. And then what we're going to do is resample those data by assuming that the particle counts per size bin are the mean of the true distribution. And those uncertainties are plus or minus a standard deviation, right? So we've got some population, we are sampling it, randomly, right? We're getting some random realization of the true population, and it can vary, our samplings can vary within the counting uncertainty in each bin. And so what I've done here in this code in line 118 is I've said, okay, I'm going to resample this 100 times. And I set up a matrix called trials that I'm going to put that into. So, so I've got a count per bin, and then I just resample it 100 times. So now I have 100 size spectra all drawn from that same mean and standard deviation. And to do that, I'm using, in this case, the function normRand in MATLAB, which is drawing random numbers from a size or from a normal distribution where you specify the mean and the standard deviation. So I just plugged in the counts in each bin and the uncertainty of the counts in each bin into that normRand function. A little thing to know, side note about MATLAB is that every time you reboot MATLAB, it's going to reseed its random number generator in the same way. So, and then the numbers that it generates have very good sort of pseudo-random statistics. But if you truly have a need for different random numbers each time you run a simulation, you need to actually tell MATLAB, okay, shuffle the generator, start over with different ones. But it's actually not, well, maybe Patrick will think of reasons that this isn't true, but I think most of the time we don't truly need a reshuffling, right? You just need numbers that have the right properties. So it's only if you really truly need each subsequent run to be different that you would need to do that. So
it doesn't matter here, but it isn't worth the number or something. It is pseudo random.
Yeah.
But it's not random. It's
yeah.
very hard to do.
Yeah, and if you want to save, and so it's based on the clock. So if I call normRand now, and then I wait 2 seconds, and I call normRand again, it's going to be a different set of random numbers, right? But so if I want to keep the first set I generated, I have to save it in some way or another, or save the seed that the clock was using, or that the generator was using. So it's just, and I don't know anything about how this is done in Python or any other. It's the same thing. Okay. There's great MATLAB help that kind of describes the different algorithms that are used to generate the pseudo-random numbers and everything, if you want to get into that. Okay, so what I've done here, I can't remember if I ran this or not, so I'm going to run it again, is I've now plotted these resampled data. And I don't know from across the room if you can see this very well. I've used a color map just to show the distance from the mean of all of these resampled data. But each dot in each column here is a different realization of the number size distribution in that bin, or the number concentration in that bin. Okay, so we've got this broad array, and as you can see, as we get out into those larger size bins that have very low particle counts, large counting uncertainty, there's quite a spread in how many particles you might see if you are sampling that size with that sample volume. Okay, so now what we're going to do is the same fitting of the power law to the data that we did before, only now we're just going to do it 100 times. So set up the initial guess of the particle counts at the reference diameter and power law slope and the reference diameter itself. And then I'm just going to loop through my 100 trials. Each time it's going to fit to to a different realization of the data and spit out a different value for the number concentration at the reference diameter and the PSD slope. And so I'm just going to save them in a vector. And then at the end, I'll take the mean and the standard deviation of all of those 100 trials outputs. And so that's going to give us the mean of the number concentration at reference diameter and particle size distribution slope, and also an uncertainty. Okay, so we can see that for these data, the PSD slope is 1.8, and the standard deviation around those different estimates is plus or minus 0.13, right? So now we can say, just based on the uncertainty in our observations, we can propagate into our fit what the uncertainty in the parameters are. This is a pretty simple example. A lot of things like this, you could do it analytically, right? So it's really just if you're lazy, or if you have a really complicated system that's nonlinear and hard to propagate analytically, this kind of technique can be helpful. Okay. And this is just a little histogram. So this is our distributions of number concentration on the left and the power law slope on the right coming out of this. So you can see there's quite a lot of variability just based on how well we can actually measure the concentration in each bin. Questions on this one? Ideas? Disagreements? Okay, I'm going to move on. So the next example I'm going to show you is this one that I wrote as a grad student. And so just as an aside, as a grad student, I studied photochemistry in turbid water. So absorption of light by little suspended sediment particles and the photochemical reactions that happened on the particles. And so I did a lot of simulations where I took beakers of muddy water and I put them in a solar simulator, and I shined a lot of full spectrum simulated sunlight into them to then measure the chemistry of what was happening. And at one point in my thesis, I needed to figure out, okay, how much of the light that I'm shooting in here is going into the beaker or out of the beaker, and how much is actually being absorbed in my turbid suspension. Because maybe I need to use different beakers or line them with a reflecting surface, or increase the concentration of the sediment so that more of the light's being absorbed by sediment and not by beaker, etc. So I wrote this model. It's probably not the most efficient way to go about doing what I was doing, but that's part of being a graduate student sometimes, is to, yeah. So my experimental setup was not plane parallel, right? My fluid medium that I was interested in was surrounded very close, right, in a beaker with nearby walls and made of glass and refractive index changes and all of that. And it was very turbid, so definitely multiple scattering, and I was actually interested in absorption, right? I wanted to know how many photons were being absorbed by the particles. Optical depth in a 5 centimeter deep or 10 centimeter deep beaker was about 1 to 2 centimeters, as you'll see in a second. I didn't actually take any photographs of my setup at all when I was a grad student, so all of these images were sourced off Google. I didn't put the beer inside the solar simulator, but it's nice for scale, so I put it there. What I'm going to do is go back over to the second folder. So this is the one that's photons in the beaker. It starts with 2_. And what I did here was I started off, this is sort of a complicated, to me it was complicated. So I started off just modeling a 2-dimensional beaker, the light going in just in one plane. And I, at first, didn't worry about interactions of the photons with the walls. I just said, here's the beaker boundary. If the photons leave, then I stop tracking them. And that's all I did. What I've done with this live script, and this is not the case in the in-file version of this, it just goes. But in the live script, I've put it in twice. The top portion, there's only one photon, so we can step through and see what's happening. And then in the bottom portion, it's going to just do everything. So first one is just comments. So the first thing I'm doing is just clearing out variables if I'm running things twice. And I'm only going to simulate one photon, as I've said. Can you guys all read this? Do I need to zoom it in more? People in the back? Good. Okay. I mentioned this was super turbid, attenuation coefficient of 15, absorption coefficient of 1. And This time through, I was lazy and didn't even scale it to proper dimensions, right? So this is actually for a fake beaker that's 1 meter wide and 2 meters tall. So the IOPs will increase in the next simulation where I use the realistic physical dimensions. So I'll run that guy to set my IOPs. And then what we're going to do is we have to get that initial radiance distribution of the light. And so I set up an angular coordinate from 0 to pi in 1800 steps. Perhaps that was overkill. I don't know, but this was, 27-year-old me. So I generated this probability distribution by integrating over the distribution of my irradiance coming in and then normalizing it to the entire as a function of angle, and then so from 0 to each angle divided by the integral from 0 to the whole distribution. So that was how I came up with this 0 to 1 probability mapping for the initial photon direction. And then I made a lookup table. And the reason I did this is it's really slow to rerun generating the probability every single time. So it's better to just make a table, interpolate into the table. It's a little bit faster. So I'm doing that both for the radiance, and I'm also doing that for the volume scattering function of the particles. And for this, I just use the Fournier-Farrand approximation for a backscattering fraction of 0.03, which is, you guys were just looking at some 0.01s and 0.02s out here offshore. So again, very turbid, highly mineral, highly scattering particles. Oh, this is just it approximated the distribution of the light. This was almost like visual. Like I was just saying, okay, here's the light distribution that SunTest says is coming out of their solar simulator. What function can I make that will generally approximate it? If I'd been really had even more time to spend down this rabbit hole, this was a rabbit hole, I probably would have gotten a radiometer, and yeah, but I didn't have one. So anyway, I choose what the manufacturer said and tried to fit a function to it. Okay. And I have a problem. I got to change folders. You guys should also do this if you haven't. You should be in the photon speaker folder. There we go. All right. And so you can see this takes a little bit to run. And then I'm just going to plot up those radiance and VSF. So this is the probability distribution for photon with a zenith angle 0 to pi over 2. And this is, 0 to pi for the scattering angle for the VSF, right? So we have a very large probability of scattering very near forward. And then as we get towards these larger angles, the probability increases much more slowly, right? So if we draw a number between 0 and 1, most of the time that's going to give us a very near forward scattering angle. And then every now and then it'll give us one that's more in the backward direction. Okay. Good. Okay. So now, for what I was doing, I wanted to track what was happening to the photons. Each photon, I see us confused. Look, let me stop. Yeah.
So what we said is that most of the experiments will be in forward direction, and then every now and then we will be in the direction, but the probability of one is higher than the
So if you draw, so the random number generator is going to pick things between 0 and 1. If it picks a number here, 0.3, 0.8 is going to have that scattering angle. 0.6, 0.7 is going to have that scattering angle. Only if it picks a number very close to 1 will it scatter in a more sideways or backwards direction.
Okay.
Clear?
Yeah.
Okay. Yeah. Okay. So before I start modeling photons, I want to make an array that's just going to say where they are and what direction they're going, and maybe some other things too. And this one, I'll keep track of the cumulative path traveled by the photon. So that's sort of the Z position here. So it's got a depth in the beaker, and it's got the third column. And sorry, the columns of my array are in random order, also not super efficient. Then we've got the horizontal X position. There is no Y position because we're only in 2 dimensions. We've got our interpolated. So I've got the sign of the photon direction from one random number. And this is again because we're in 2 dimensions, right? So the photon coming in reality should have a zenith and an azimuth, but I've only got the zenith. So I'm just choosing plus or minus for the azimuth. And then in a later version of this, I'll switch that and do another angle to model the direction of the photon. And then the photon has got X and Z position. Z is always at the starting at the top, so 0. I think that's it. Cumulative distance traveled, 0 to start with. And then I'll keep track of some things as we go along. And then the initial radiance distribution, also save that. So run this guy. And then this part will, in the next run of this, will be in a loop. But here I've just commented out the part that there's a while loop in there. So it's basically check to see if the photon should keep going. Here we're just gonna let it keep going and we'll stop manually. So we start with our tracking variables reset. And then what we're gonna do is, I called it dice because I was clever. I'm gonna generate 6 random numbers. And those are going to cause the photon to move in the Z direction and the X direction. They're going to move according to random number minus of the log of the random number over the beam attenuation coefficient. Second random number will take the sine and the cosine of that to figure out the X and the Z motion, and then add that to the previous position. And then compute the cumulative distance traveled. And also track the path so we can plot it later. Okay, so we've got our new state array of the photon. So if we run the next bit here, it's basically just an if, else loop or conditional that's going to check and see whether the photon has landed outside the beaker, right? And I've set a beaker whose walls are at 0 to 2, 0 to 1 in the vertical direction, whether it has been absorbed or whether it's been scattered. And I had it output what happened down here. So in this case, it was scattered. So now we're going to move track event, increment that up 1, and actually go back and rerun, right? So we're in this loop now. I'm doing it manually. I probably don't need to keep doing this. Hopefully, it won't take that many to get it to quit. It did take me 20 when I was testing this yesterday. While I'm doing this, does anyone have questions? Great. Absorbed, fantastic. Okay, so it's taken 5 steps along the way, and we record everything, some useful descriptions of what those arrays mean, and then plot the photon path. So here's my all-form beaker, extra large, real dimensions, and you can see the path of that photon as it goes in until it finally gets absorbed. On a plot that isn't really necessary at this point, but that's where it's absorbed. So now we're going to do the same thing again, and this time we're going to do it for 1,000 photons all at once. Okay. So right now it's a little bit slow because it's figuring out that distribution for radiance in the VSF. Here's our initial photon distribution, right? So this is sort of our zenith angle distribution that we expect inside this reflecting wall solar simulator. And now we can go through and run the whole thing and plot it up. Okay, so I've only plotted the first 10. One thing that inefficient coding can do is make it difficult to, if you try and save everything, you can't actually save everything. So I just had it save 10. So here's 10 photons and their paths and my turbid water fluid. So you can already see, okay, light penetration, pretty small, right? Most of the scattering and absorption are happening in the upper few centimeters. Yeah. It went out through the wall. This one here,
Yeah.
that one,
No,
this one. So it went out. It went out. I should figure out why it starts there, but I'm pretty sure it started inside because they all start here. This is the distribution of where they died. And again, no interaction with the walls, just inside or outside. Cumulative path, right? So you can see that the ones that do make it to the bottom of the beaker they have a very amplified path. They traveled around 3 meters in a 2 meter deep beaker, right? So you could imagine doing this for particles inside a filter pad and an integrating sphere or something like that. Yeah.
I'm just a little confused. So the photons that die are outside the beaker. There's also outside the beaker.
No, it's just it's an incomplete simulation, right? So at this point, I have not added any properties of the walls.
Okay.
Anything that ends up outside the beaker, like in reality, would have hit the beaker wall, and then something would have happened. Here, I'm just saying, I'm too slow. I'm still figuring it out. I'm just gonna only do the fluid, add the walls in the next step, which I'll show you in the second
Okay.
code. Yeah.
Okay.
So if it's outside, something happened, but I haven't modeled that.
Okay.
Is the point here. Yeah.
In the plot right before this, each dot along the lines of scattering event.
Yeah. Or an attenuation event. Right. So we model, so the distances it travels are modeled as minus log of the random number over the beam attenuation. So that's saying, okay, it goes this far, and then an attenuation event happens, and then you roll another die to figure out if that event is an absorption event or a scattering event.
Okay, so the reason that some of the lines don't exactly.
Yeah.
match the top is because it hasn't hit that.
Yeah. 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 My EZ, DZ is minus log of random number 0 to 1 divided by beam attenuation. Yeah. Okay, so this is the 2-dimensional with no interaction with the walls. So then the next one, all I do, it's the same simulation, only this time I'm gonna do 2 things that are new. One is I'm putting in, and this is in the block from 15 to 17, I put in some depths where it's gonna call an external function that's gonna basically be a radiometer, right? So now I'm gonna measure the radiance at depth intervals going down through my beaker. Oh, I'm also using real dimensions. So this is my real attenuation and absorption coefficient, and that was about right for the suspensions I was measuring. And the beaker dimensions are 10 centimeters deep by 5 centimeters in diameter. The other thing that I'll do is also call this beaker wall function. And where do I call it? Here. So in line 82, if the photon is outside the beaker, then we figure out where did it cross the beaker wall, and then plug all that information into this external function beaker wall, which contains things like the refractive indices of the wall and a very, very unelegant way of figuring out geometrically where does it go, how does it get bounced off, what's the transmission, the Fresnel transmission through the wall. So I'm not going to take you through this function just in the interest of time, but you're welcome to look at it. Perhaps you'll find something I did wrong. But yeah, so there's a beaker wall, and then the other one is the radiometers. So detector is this guy here. So we've got light meter depths, photon information, where it is, which direction it's going, what track event is it, and then it's just going to go through, and we've got a detector that's set up to be exactly the full area of the beaker. It's just like an imaginary circle. You don't have to worry about detectors shading each other in a Monte Carlo simulation. They just are wherever you want them to be. And it's just looking at whether the photon crosses the plane of the detector. So it's a scalar irradiance detector. You could put in a cosine response. There's a commented outline here that would turn that into a cosine collector. So you can make your detectors be anything you want. Okay, so we're going to go back to the 2D bounded and run it again. And this is 1,000 photons, which isn't really enough to do as good of statistics as you want, but it's very inefficiently coded. So I'm not going to run more than 1,000 here in class. And as I'll talk about at the end of this lecture, there's a lot of things you can do to speed up simulations like this. So here's 1,000 photon tracks in the 2-dimensional beaker, and this time they interact with the walls. So either they're transmitted out, they're reflected back in, based on the properties of the wall. And you can still see, even when we do this, there's still, most of the light is really contained up at the top of the simulation. Now we have our walls doing stuff. So now we don't have any absorption locations that are outside the beaker. Instead, they either get absorbed along the wall or within the fluid. Some information that's also coming out of here that's not that important for this discussion, but it's in the workspace if you look, is how many photons are absorbed by the walls versus in the fluid. And so from this simulation, I was able to figure out, oh, wow, half my light's not being absorbed in my experimental solution. Maybe I'd better do something different about my beaker container design and optical properties, or maybe I need to use a better model than actually, or in this case, I actually put in actinometers, which are chemical light sensors to tell how much light was getting. So no, it wasn't necessarily absorbing. Yeah, actually, because I think because of the angle of incidence, right? Because it was so turbid, right? You don't have any glancing angles. There's a lot of, yeah. And the last thing that you can do with a string of light meters or radiometers in your hypothetical beaker is you can plot your scalar irradiance distribution, right? And so this is actually, you know, the getting towards the information I actually wanted for my photochemistry, where I needed to normalize to absorption, reaction rates to absorption. Okay. So that's the bounded 2D version. And now I move to my 3-dimensional simulation. So at this point, most of the difficult work was actually done. It's just a matter of putting in another angle for both the photon, well, another coordinate for the photon position, another angle for its direction, another angle for the initial light direction. And it's a lot slower. So you can read through this if you'd like to see how I moved from 2D to 3D, but basically it's just inserting more random numbers to account for the whole thing and making more complicated plots at the end. So we're gonna loop through again. So you can see, I guess I'll stop for a second and just point out one thing, which is that in order to, at least in order for me at the time to figure out how to move the photons through real Cartesian space, I was keeping track of them in polar and cylindrical coordinates, right? But I wanted to actually move them in Cartesian space and, you know, calculate angles and things. So I did a whole lot of back and forth between polar and Cartesian. That probably wasn't very elegant. I think is this the most elegant way I inserted a couple of days ago for this class. So there's a whole lot of things you could probably do to this code to make it faster. Okay, that's done. And you'll notice, I don't know if you guys in MATLAB, there's a function called tick and tock, which you can use to mark the beginning of an execution and the end. You don't need it for 1,000 photons. And actually, you don't even really need it for more photons on this computer, but 15 years ago, you did. So that's also just something, a good thing to know sometimes. So these plots are more complicated. It'll take a second to come up. I think I ran it. Come on. Huh.
Well, that's the risk of doing like.
Oh my goodness. Why? No, it should be in line.
I think
If you put out the red side, there's like that strip there, the second.
Oh.
box. Yeah.
Weird. I don't know why I did that. I said it. I thought I saved it to put it. Oh well. So if it will let me interact with my figure, I'm asking my computer to do a lot right now. Should be able to rotate it around. So this is the downward view into the beaker and the first 100 plots, but you can, yeah, look at where the photons went in your non-plane parallel radiative transfer simulation. It's kind of fun. Same thing for where the photons were absorbed in the beaker. Again, very close to the top. And then finally, the scalar irradiance profile within the beaker. So anyway, this is just an example. It's not an example of good coding. It's not an example of efficient Monte Carlo simulations, but it is an example of how to build something with increasing complexity. And particularly because the reason you want to use Monte Carlo simulations is often because you've got a really complex system, sensor versus light kind of thing that you need to model. Okay, so I'm gonna switch back over here. Okay, actually, I'm not gonna switch over here. I'm gonna stay in MATLAB. The last example I'm gonna take you guys through is this example from a report that was written by Leathers et al. Kurt Mobley was one of the authors on this. And it's a great, the link is in the lecture slides for today, but it's a really nice sort of tutorial on using radiative or using Monte Carlo simulations to model radiative transfer in different sorts of situations. So this is their example 10.5, which is based on an original model that was written in Fortran in 1981. Leathers et al. Put it into MATLAB, and then I just turned it into a live script and added some figures and a little bit of explanatory text. But it's a nice, simple, this is plane parallel, optically deep light field or water body. So we're looking at the light field in that. So to start off with, I am going to clear out my workspace and change to the Leathers 04 example. So this is the one that starts _3. And there's two versions of the M file in here, I should mention. One has just got my figures, and I put in some additional radiometers that weren't in there originally. The initial example is just in the Leathers 04 example 10.5 you can look at. Okay. So the way that the IOPs are set up in this simulation, we have a beam attenuation coefficient, and then we have the single scattering albedo, so B/C. A little more condensed than what I was using in my earlier ones. And then they've modeled the volume scattering function using a Henyey-Greenstein phase function, which you can see. I pulled this equation and figure out of the Mobley Oceanic Optics textbook, just to illustrate. I don't remember if Wayne talked about this in week 1, or if you remember anything from week 1, or if your brains have started leaking out your ears. So this is just, it's an old, simple way of approximating the volume scattering function. So the green, red, and blue lines here are different parameterizations of a Henyey-Greenstein function. And there's this parameter G. If you increase that from 0 to 1, you go from an isotropic VSF to one that's very highly peaked in the forward direction. So that's basically how it works. Compared to the black line here is the Petzold San Diego harbor measurements. So you can see that it kind of gets the slope right in the middle angles. It doesn't really get the highly peaked nature in the forward direction, and it doesn't get the little flip upwards in the backscattering, the very high angles of backscattering. So it's a decent approximation. It's fast to compute, but you could probably improve this maybe by plugging in a different VSF and using a lookup table if you wanted to do that. So, so here we've got our, so I've just run a bunch of stuff actually in the single section. So the water IOPs, the parameterization of our phase function, also the relative index of refraction of water, and the critical angle for internal reflection. So here, this model is going to put light in, and then if it bounces back up, and this wasn't in my beaker model, right? But if it hits the air-water interface from below, it's going to determine whether or not it should be transmitted out or reflected back in. So that's what that's for. These are vectors that show the depths where we've got both upwelling and downwelling radiometers, and then how many photons to simulate. And in this case, there's no, so in my other model, because it was a bounded model, right? Photon left the beaker or got absorbed, we stopped modeling it. Here, it's plain parallel, right? It could go on forever and ever and ever. So we have to tell the model when to stop so that, you know, we get answers. So in this case, they're saying scatter or track 100 scattering events per photon. Don't go on to infinity. So this is how they sort of end each photon in this model. I mean, you might want to pay attention to your IOPs that you've put in and make sure that the number of scatters that you're tracking per photon makes sense. Okay, so here as in the beaker model, I'm going to start off by just initializing things that I'm going to record as I go on, and a structure. In this case, this is something I added, is just to save the tracks of the photons as you go along for the first 10 in this case, so we can look at them later. All right. And so this entire block, it's all one block. I've put some comments in that I'll go through first. So we're going to loop through the 10,000 photons that we're going to simulate. And it's in air to start with and needs to go in past the air-water interface. So we're already allowing, this also has reflection off the surface from above, right? Which is different than the beaker model that I did. So photons that enter the water are going to lose a little bit in that transmission, right? As they go from the higher or the lower to higher index. And so in this model, there's also this variable W, which is the photon weight. So we're going to start off with photon weights of 1. And as they are absorbed or a little bit lost as they get transmitted through, rather than modeling a whole bunch of photons and whether they get absorbed or reflected or their intensity lost individually, we're just going to decrease, we're going to model it once and decrease the weight of that photon. So it's a way of increasing the computational efficiency. So there's a loss of W that can happen depending on the angle that it's being transmitted through. Then when the photon is in the water, for the first I photons, we're going to save the track for plotting later. I'm not going to do that for all of them. And then what it's going to calculate is how far the photon moves to its first attenuation event. So here again, we're modeling the direction, the distance it goes is minus log of random number over C. Here it's just a single random number being generated, rand. Move the photon. Check if it's gone past, it's going initially downward potentially. So first check whether it's passing upwelling irradiance sensors. So loop through all the depths we're tracking. Log it if we need to. If it's going upwards, account for that interaction. So find out whether it exits or is reflected internally and comes back down. Then check if it passes any downwelling irradiance sensors, log it if it did. And then finally, because we're at an attenuation event, compute whether it's scattered or absorbed, or in this model, it's actually doing both at once to save a little bit of computational time again, right? So we've got this W0, which is the single scattering albedo. So we're going to decrease the photon weight by the amount that the fraction that got absorbed, and then the fraction that didn't is going to get redirected through scattering. And so we update the angle for the scattering event based on the Henry-Greenstein scattering. So that's how that's going to work. I'll run the whole thing. It's very fast for 10,000 photons, written in Fortran in 1981, much more elegant than I did. And we can track the depth versus time of those first 10 photons. So depth in meters, scattering event number is all I've got on the x-axis. So we're not saving position, right? We're not actually working in a physical space here except for the depth coordinate. But we can see how these photons move around as they go down in the water or get reflected or scattered back up. And then we can also make a figure for the irradiance profiles, both ED and EU. And these radiometers are again just set up as the photon passes the depth, it gets logged. Doesn't care what direction, so it's scalar irradiance here. Labeled ED and EU, which is a mistake. Should be EOD, EOU.
It's scalar light.
Let me go back and look at those
Scalar load.
So EOD is photons that are coming down and impinging on sort of the upward looking hemisphere, right? So EO would be from all directions, but because we're looking at photons coming down and then we're looking at photons coming up, they're separated. Yeah, and the photon, yeah, it's just checking the depth. Yeah, there's no cosine response, so it has to be scalar. So yeah. Why it's really slow to update the legend here. Oh well. Okay. Wow, MATLAB's unhappy with me. There we go. Okay. Oh, the figure's good. Okay. So this particular model, according to Leathers et al. And their description of this, they actually compared this to hydrolyte output with the same setup and said, oh, it agrees pretty well. But that's kind of, if you're interested in Monte Carlo modeling or playing around with the simulation, I encourage you to putz around with it, change the VSF, change how that's parameterized, see if you can get it to agree with hydrolyte in increasingly challenging situations. One nice thing about this model is it's free. So depending on how well you can get it to match up, it might be a useful thing to play around with. Okay. Any questions on this particular script or any of the other scripts that I just walked you through? Yes, Luke.
What are, in terms of like the knobs you can turn on this model?
Yeah. So the knobs you can turn are up at the top. So IOPs, if you stick with the Henry-Greenstein VSF, you can play around with that G factor to change the directionality of the VSF of the particles. You can mess around with the single scattering albedo and the attenuation coefficient to change the proportion of absorption and scattering or the overall amount of attenuation. You could, if you wanted to, change the scattering function altogether. And to do that, you need to go down to this section at line 86, where we're actually computing the scattering and absorption after each event. So that's where this Henry-Greenstein function is actually in the code, right? So you could replace mu, which is your scattering angle, with whatever else you want. But this one is, you could put a lookup table in there, right? So here is the random number that gets drawn to choose the scattering direction. You can figure out how you want to map that to your own VSF and put that in. So you can play with IOPs. You could, if you change that enough, you could also mess around with the number of scatters that you're tracking, right? So like, how long does it take you to get to an isotropic distribution, right? If you're not at that isotropic or infinite sort of irradiance, then you may or may not match hydrolite, right? Which is going to solve everything analytically. You could change the detectors you're using, right? Instead of scalar, you put a cosine response into your detector loops, which are also farther down. So the upwelling detectors and the downwelling detectors. You really wanted to get, I mean, I would say sticking with optically deep, plane parallel is probably the way to start comparing it to hydrolite. But if you really wanted to get fancy, you could put in a reflecting bottom, right? And give that IOPs, but maybe just start without the bottom. Yeah. Okay. Okay. So, okay. So I mentioned a couple of times that that computational efficiency can be important with these. Remember, you do have to model enough photons that you're converging on a solution that's consistent. So ways to improve this, model, as the letters example did, model populations of photons with weights instead of individual photons. Also, one really important technique that gets used is sometimes called inverse Monte Carlo modeling. So you, instead of starting with an initial radiance distribution and then following things until they get to a detector, instead you start from your detector and you model backwards, right? A photon that goes from source to detector can go from detector back to source in the same medium, same IOPs. And so then you're only modeling the ones that are detected, and you can speed things up that way. When I use Monte Carlo modeling to track particles settling through turbulence, I usually start with the ones that are collected and then go backwards, just because you have to model far fewer. You can also, as I did in the beaker example, use lookup tables to map your probability functions onto random number distributions instead of computing that every single time. And as I found when I reran the thing I wrote in grad school, that took like a really long time to run. Computers keep getting faster. So maybe you don't have to worry about any of this, depending on your application, or just find a fast computer in the cloud somewhere. And yeah. So that's all I have for you guys. That took about an hour, I guess. I wasn't sure, but yeah. Questions about Monte Carlo? All right. Well, we have a little break before lunch then. Thanks.